We can start right now?
Sure.
Okay. So hello everyone. So welcome to our this month's CIS-wide webinar. And today we are very glad to have the Professor Tinosh Mohensin from the Johns Hopkins University to give us this talk. And before we move to the talk session, I want to use very few minutes to uh, to introduce a little bit about the CISS education activities. And CASIS key education goal is to become a major resource for the choice for learners across the different fields who are interested in the CAS fields of the interest. And this talk actually is part of our various programs held by the CASIS, and including the distinguished lecture programs, the industry distinguished lecture programs, and so on. And within the CAS, actually, you can access to many education resources, and there's many benefits to learning with the CAS, including the earned credits, credentials, and many job and graduate student opportunities. And if you have any questions and want to know more information and would like to join the cast, so you can visit our website and also contact our operation manager. And now it's time for our speaker to give us this talk. And here's some brief bio for our speaker. Tinosh is currently associate professor in the Department of Electrical and Computer Engineering in the Johns Hopkins University, and she also have many affiliations within the Johns Hopkins. Sorry.
I think that's good enough.
No, yeah. Oh. Okay, here. Um, she directs the energy efficient high performance computing lab, and her research focus on energy efficient computing for signal processing, machine learning, and multimodality AI with applications in autonomous systems, health monitoring, and the cyber physics system. And her work has been recognized through over 200 peer-reviewed publications and numerous awards, including the prestigious NSF Career Award, Amazon Research Award, and Johns Hopkins Bloomberg Nexus Award, and so on. And Tinosh, I know you have held a lot of the leadership in many conferences, and including the GSVSI IEEE Circuit Systems Symposium, and so on. And also give a lot of the keynotes, speak talks in numerous conferences. And okay, so now let's welcome our speaker, Professor Tinosh Mohensin, to give us this talk, Physical AI at the Edge.
Thank you, Bo, for a generous introduction. Good morning, good afternoon, good night. Today, I will be very happy to give a little of this discussion and presentation that how we can make and explore with advances of these algorithms, hardware, and system code design, we can enable robots to translate raw sensor data into real-world actions while running locally on their hardware. So I'm going to start my slides. So here's the outline of my talk. So I'm going to start with the motivation and emerging physical AI and computing. And particularly, we're going to talk about three major key kind of algorithm and hardware code design that it can put together this physical AI system to work in real world. So let's just start with a little of the more futuristic robotics. Imagine we are in the middle of disasters where the communications is down and time is very critical to figure out that where the victims are. Medics are very limited, and rescue team, we are very searching to find the victims and assist. So in these times, usually where the communications are down, so any little help from any type of device would be significantly help. impactful. And that's basically the vision that I'm seeing it in my lab. And the idea here is that so how we can make these devices that they require to perform multimodal perceptions, audio, reaction, and to the environments, everything being done and performed in the edge devices without the need to connect it to the clouds. So think about robots as the basically physical systems that they have two major parts. One is their heart or their body, which similar to our body, which has the actual hardware and the sensor. And the other part is their brain, which is basically nowadays this advanced AI is trying to enhance their capabilities. So with the advancement of these artificial intelligence, we are able to perform a lot of modal sensing, including, so for example, and perception, including, integrating text, image, audio, somewhat similar to the way that our human body and the brain works. However, unlike the human brains and body that you're totally integrated in a whole system where basically the AI and the body reactions are working perfectly together, these advanced AIs completely staying somewhere else. So these advanced AIs heavily rely on the very heavy infrastructures because they require megawatts of the power, terabytes of memory and storage. And usually when we are talking about, for example, these huge large language models, vision language models, they not necessarily need to be real time, However, on the other hand, in these type of the robotics that, for example, some examples in my lab, for example, for the drones or the leg robot or the wheel robots, they need to constantly sense and perform in the real-time reactions. For example, the drone that it's basically flying and is capturing the images from its input camera, it needs to basically stop and avoid this basically crashing to the person immediately. So there is no time to find that, for example, send the raw data to the cloud and wait for the latency of the processing and data back to the cloud to perform the action. So basically for today, I want to walk you through to see how we can make this advanced AI that are sitting on all the way on the left side of this pod to move them back to running on these tiny devices. So just looking at these large models that we are talking, for example, for the large language models, which basically their size is already also exceeding the capacity of the server-like memories. For example, as you know that the GPTs or Llama, so they're already much bigger than the, for example, A100 type of GPUs. But what we are basically right now focusing is more on the embedded type of hardware like the Jetson or Nano, Raspberry Pi, GAP8 processor, which are coming with very limited memory. And then also they are following the memory hierarchy that usually is available in other systems too. So the closer memory to the processor provides much better speed in terms of processing. But as you can see here, these are coming with a very limited space. So even though if we make for example, these large language models smaller, for example, use a 4-bit Llama or 5 to 4-bit model and deploy them in this type of devices, they're still actually slow and they're still taking a lot of power consumption compared to other parts of the systems. For example, the object detection and YOLO. So this plot on the bottom left shows the power consumption over the time as from the time that we load the large language model on the system, on this robot, and giving a prompt, which basically you see a big spike on the power consumption of the board, and then generating the actions, because large language model nowadays is being used for basically, for example, planning for the robots. So as you can see, that there are two major trends here. So one is that there is a large power consumption, which basically compared to YOLO object detection is about 2 times bigger, but then also is slow because these devices are very relatively, as I said, compute computation wise, it's weaker, and also in terms of the memory and hierarchy call of the memory, so it's very, very small. So therefore, it needs a lot of memory transactions from the larger size of the memory to this near processor. So that's basically the issue comes, and therefore not only just designing the algorithms for smaller models is important, but also designing a hardware-aware model that it can fit in this type of resource constraint architectures. So my lab, energy efficient high performance computing, has been working on this for several years, starting from signal processing to nowadays with these advanced AI and physical robots, to show that how, again, hardware and algorithm and system design can enable these type of robots be able to work constantly and continuously and reliably to perform and address the needs of, for example, now every day. So, for example, if you can either use the robots for example, bring you a cup and do some maybe kitchen work, or basically ask a robot to go out and check, for example, the mail for you. So they should be constantly be able to perform this in real time. So that's basically where I'm gonna focus today. But before basically getting to a little more details of the actual, more on the model architecture design system integration, I want to just basically walk you through what are the steps that we do. So again, as you can see here, once we've learned how to do it, we can also expand it to multi-agent, multi-robot coordination. But the key thing here is that what I want to focus is this kind of architecture on the right side, that from the time that basically robot sees and or basically senses some different inputs, for example, from its camera or from its, for example, audio or LiDAR, radar, that's basically where the inputs or the state going to the basically the whole overall system. And the part that we are basically focusing in maybe is the part that is performing the planning. For example, it could be a large language model or a reinforcement learning is performing the planning for what the robot does. And the low-level planner or low-level policy is the one that performs the task. For example, go to left, go to right. And these are usually, again, is trained, each of them independently, for example, with several different methods, for example, reinforcement learning, or nowadays a lot of these end-to-end architectures like vision language models. But at the end, what we care in terms of we as a circuits and systems society, we care about the operations. We care about how we can make these put together into systems and hardware. So that's why basically I want to quickly walk you through from three key essentials that nowadays people actually are trying to use it in this type of robotic system, how we can make them very efficient, and how eventually we can get them together to be working in an actual real world. So MAGRIP is the first subject, magnitude and gradient informed compression for task agnostic large language models. So I assume that many of us already have interacted with large language models, but in order to get to understand that where is the, again, the computation, the memory, and where the optimization comes from, so I just want to quickly go over these layers of the transformer models, which is found both in large language model vision transformers, which is basically consists of mainly the multi-head attentions and feed-forward layers, and obviously again the transformer functions come with the encoder and decoder. So encoder and decoder both have these type of blocks. So again, multi-head attention, feed-forward layers, and I'm gonna just focus on these two, mainly these parts that I can tell you, so how we can make them more efficient. So for the feed-forward layers, which is basically mostly layers of the fully connected networks, and the attention layers, which are again computation of the multiple key query and V for the different matrices and matrix operations. So again, eventually, just basically you need to think about all of these as variety of different types of matrix operations, but many of them. That's the key thing. So for example, for the llama to 7 billion model, we are talking about the multi-head attention about 1.6 billion and feed-forward layer 4.6 billion. So now what I would like to kind of a little go into more details is that, so when you look at these multi-head attention layers, as I just said that, so there are multiple linear matrices of the matrix operations that is happening. And the feed-forward layer, which is kind of a little simpler operation, we can focus on that for the first part of the talk, is basically two network of fully connected layers. And the idea here is that if we want to, for example, focus on reducing the size of this part, we can imagine this one or model it as a graph with edges and the neurons, where we want to find a smaller subgraphs where basically still perform the same perceptions or reasoning, but with much, much smaller size. Okay, so let's just quickly review what we are talking about in terms of compression reduction techniques. So again, as I said, let's just think about, again, all these operations with variety of different these matrix operations, matrix sizes, transpose, inversion. But the key thing is that at the end, we need to deal with all these number of entries. So therefore, if there is basically a fully connected network model with one of these matrices, so we can basically quantize the models where represented with less number of bits. We can extremely quantize them to basically represent them as a very low bit, like only 2 bits. We can also reduce the number of the edges, where basically it ends up with this type of representation. However, this representation shows a irregular parent representation of the entries. So in order to address to the memory addresses of these entries, so we basically make the structure. So these are all traditional techniques that over the several years for even any other type of signal processing, people have done that. But the point here is that what I'm trying to show is how we can combine these compression techniques together and how you can make the overall model size much more compact and without basically reducing the accuracy. So I'm just showing you one quick example. Think about this model here, a fully connected layer, where I'm showing the number of operations on the y-axis and the model size on the x-axis, starting with a 98% accuracy. So when you prune the model, so you can actually get about 24 times reduction, a randomly pruned model. But when considering the requirement for memory to index these elements, so you get basically almost 12 times reduction. So, and you see very good, relatively good accuracy. So the structurally pruned or structurally sparse certification, it kind of reduces the number of edges. But the key thing here is that since we reproduce or introduce this structural architecture of the model, so we don't need to have the memory index. So therefore, overall, we reduce it by 20 times. So now what I'm just showing is that let's combine the extreme quantized, like the ternarized model, with this type of pruning. So with the ternarized, basically we are showing that every 32-bit weight with 2-bit, representing with 2-bit. So that means that by default, we are getting about 16 times reduction with some accuracy loss. And now we are combining the pruned and ternarized However, since the prune still requires that index memory, the reduction, it just becomes only 20 times. But when we use the structurally sparse and the extreme ternarize model, we are getting 20 times reduction from the structurally sparse and 16 times from the ternarize. So we get to get a 320 times reduction theoretically. Okay, so basically from that basically makes you a model to run potentially in a microcontroller. And that's basically, we are showing the model here, that this is basically how you can potentially get the model reduced. And that's basically where you can show the impact on this type of physical system, because the next is that how to actually deploy it, which I'm gonna walk you through it a little later, but I just want to show you first this the impact, where basically on the left side, the model, which was a convolutional neural network, was running on the cloud. Basically, the camera input images that was coming from the drone was constantly being transferred to the cloud, and the cloud was sending the decision to the drone to, for example, stop. But what is happening is that when the drone is going basically keep getting away from the source of the processing, which is here, for example, could be a laptop, eventually it loses the connection and it just kind of cannot become operational. On the right side, we significantly reduce the model, so we perform all the processing, sensing, and action on the drone. So without the need for the use of any other connection to the laptop or to the cloud. And that's basically the significance of this type of extreme compressions and improvement of the performance comes. So as I just said, so there is a lot of work has been done, so since several years ago, particularly for the work that I'm showing. The key point that we our Maghrib is showing is the hardware aware pruning, and obviously is a structurally sparse pruning of this. So therefore, Maghrib architecture, which is basically taking the basic large language models and particularly for the feed-forward layer, FFN layer of the large language models, given the particular hardware resources that we want. So therefore, one of the key inputs that we are basically taking in part is the availability of different parameters of the hardware that we want to run it. And I just mentioned that, so there could be many different hierarchy and different types of the hardware. For example, maybe Amazon Trainium, ARM, the NVIDIA Jetson Orin. So therefore, they are all coming from different architecture. So this part is a key role, playing a key role to tell, for example, one configuration that we want, for example, model size. And the part that we are basically focusing is that designing a mask for this feed-forward fully connected basically layer, that mask is learned through a two layer of the optimization, which is the L2 norm calculation and fine saliency calculation with regards to the size of the model, size of the available hardware memory size. And therefore, eventually, it gives you a mask that where you multiply, and this is in the training, it gives you a sparse network. Okay. And the key thing here is that, so once you do this, which is basically, it looks very easy, but it doesn't take, it takes very, very long time, and it takes a lot of resources to train. For example, these experiments were done, run on the NVIDIA A100 GPU, and for a couple of days for different smaller, basically, models like the Gemma, Llama, Gemma 2 billion, Llama 8 billion, and GPT-2, which was again a smaller size. And it's basically the results that we are showing after the pruning. we basically adapted for the different data sets, which this one particularly is for medical questioning answering, because what I want to show you next is that this type of pruned LLM models can get to the actual real system. So for example, here it just shows that as much as the pruning that we can do on the right, on the bottom side of the these two plots, so obviously the accuracy decrease. And here the accuracy score for the large language model, there are many different scores. Here we are just using perplexity. Perplexity is, think about a little of the inverse of the accuracy, basically how surprised the model becomes for predicting the next tokens. And so therefore, the larger perplexity is worse. Okay, so therefore, obviously, as the amount of the pruning percentage goes higher, the accuracy gets less. However, there are a couple of key trends here. So the two data sets that we are using, MedQuad and Medical and Mido, they both are two different questioning answering data sets. And in order to show the accuracy of and performance of this prune model, we are basically performing four different configurations. So fine-tuned on MedQuad and tested on MedQuad. Obviously, that usually gives a better answer, right? But because it just does both of them. And the other thing is that, so medical middle, which is basically the larger data set, does a better accuracy when for this pruning. And then you also mix and match, so in testing and fine tuning to explore all these different cross data sets, and then you can make it ready, prepared for the real deployment. So here I'm just showing the accuracy, showing the power consumption when you deploy these models on the GPUs, and these GPUs are Jetson Orin GPUs that are available on this robots. This robot is a Unity go-to EDO. We're going to show it a little later. But again, the result shows that, first of all, the original model, which was not able to run it on this because it was very large size. So now with the smaller size, we are getting about 5 to 5.3 to 5.6 times reduction overall for the model size. And we are able to run it on the GPU. And this is basically what it shows on the left side, which is basically the total power consumption for every query or prompt that we are sending. So basically about, say, 12 queries, and you can still see there is a big jump, which I was just showing it at the first few slides of my talk. And that's basically where is the total power consumption comes, including the system. So now the next thing here is that, so what I just mentioned is that we basically we did the pruning of the model, but we ran it on the available off-the-shelf hardware. But the key benefit here comes that when you also design your hardware, because then you exactly know that how you can basically make the number of the parallel processors that you want to run these matrix multiplications, and for example, either fully connected or the attention layers, you can play with the number of the memory read and writes in terms of the width of the memories. Because, for example, if you build it on the FPGA or an ASIC, you can basically have configuration, all of them. And then you can find what would be the best configuration for this type of architecture, which usually you cannot do it on this type of GPUs because they are already hardware implemented. And that's where basically the work of my PhD student shows that basically you can come up with total different number of the processing elements and different memory read and write widths or memory sizes, which you can optimize the performance and the power number and come up with the configuration in the hardware that gives you the best energy efficiency in terms of GOPS per joule. And then you can design that one for the hardware. And that's what we did a couple of years ago. So basically, we built the FPGA, but then later we built the chip, and we demonstrated at ISCC conference, where my student won the best demo award of this demonstration, which was for the basically handwritten, digit recognition. And that's basically shows that, the combination of hardware-aware architectures and design, it gives you a very good grasp of the best energy efficiency. And that actually, again, comes with the algorithm architecture and design. It comes from the, not necessarily now from this new advanced AI, many years ago, so for example, this message passing, the error correction type of architecture, they have the similar type of similar architecture. So you just need to come up with the details of what would be the algorithm, what would be the graph, and come up with the best, for example, partitioning techniques that eventually gives you the best solution and the best architecture and hardware implementation in the at the hardware. Okay, so now I just want to now that was the, for example, large language model, the fully connected layers. Now I want to mainly focus on the next part, which is nowadays very important, vision. And particularly, I want to focus on the, again, compression of these vision transformers, and for an example of the medical AI assistant. So in vision, again, we are looking again, same thing, vision transformers, Mamba visions, convolutional neural network. But let's just quickly just look at for another data sets like, or domains, medical imaging. In the domain of medical imaging, MedMNIST is a popular benchmark that categorizes about 14 different medical imaging modalities. And maybe I can answer questions after the talk. So I will be really happy to talk about all of them. And we can obviously, classify different imaging modalities like the X-ray, pathology, ultrasound, and that's basically on the right side. Basically shows that what is the state of the art model performance on these type of data sets, starting with the ResNet that actually designed for this particular data sets a couple of years ago. As you can see, it has a smaller size, but also the accuracy, which is on the y-axis, is relatively low. So more advanced transformer functions like both Mamba and Vision Transformer, they significantly improve the accuracy, but also the size and the operations are becoming larger, right? So which makes sense. So the better models usually they come with much more complex layers or more number of the layers. So therefore, it just basically that there is a always this balance of the accuracy and the size. However, when we want to run them on these type of physical systems, as I just mentioned, we are dealing with this memory hierarchy and the compute problem that we looked at it earlier. Although these type of GPUs, the Jetson-Orin GPUs, they provide very high throughput operations, so terabytes. However, since they are basically dealing with these large sizes of these memories, large size of models, and there is always a need to save them into the more kind of further away memory hierarchy. So there will be a lot of latency coming from the memory transactions. And again, so it makes sense if you come up with a kind of a representation of these models that they can reduce this type of transactions between this larger memory hierarchy and slower memory to basically smaller and faster memory. And that's where basically the BitMet VIT, which was recently published at ICCAT, is showing the work. So again, going back to the vision transformers, as I mentioned, there are mainly three main parts: the embedding layers and positioning of each of these patches, and the encoder, where basically learns the features of these patches, each patches individually, and obviously preferably we are doing all of them in parallel. But again, into these major two main operations. So attention layers and feed forward layers. In our work in BitMed VIT, we are basically doing these three contributions that gives you a working system together. One is that multi-query attention, which is basically grouping the key and values of the attention matrices for sharing. So therefore, we are reducing the amount of total storage for these matrices. And for the feed-forward layers, we are reducing the each way to 2-bit, and we storing them, for example, 16 of them per each memory write. But then lastly, which is the part that was also making an important essential role, is that since we wanted to run this on the robot and the GPU robot, so we have to actually go on in more details of designing actual kernels for the GPU that perform this type of bit packing, like a 2-bit packing and unpacking to run them on these GPUs. So just quickly going the multi-query attention, which has been, as I said, done for several years, is that in the attention layers, we are performing this particular operation, which is a softmax of query of the key transpose of the dimensions and by each basically value. So in the multi-query or group query, those type of operations, basically the idea here is that you share the value and key for the queries, and you therefore you don't save the operation, you save the memory, right? Because you save only this much instead of this much. So basically h times, for example, here for the head, you can reduce the total size. And then again, similar for the previous work that I just showed here, I'm just showing a little more details for the feed forward and the attention layers. If you want to perform the quantization of the, for example, extreme bit quantization, you want to see where is the best compacting solution comes. So therefore, it's always great to see within the models that you're looking, within the layers of your models, you figure out that what will be the size of these layers. For example, it shows for this type of med vision transformer, 6 million is for the fully connected, and 1.8 million attention. It will be really great that if you quantize this and basically pack them, so compact them for 2-bit, and then figure out how make also the accuracy back. So this just goes a little more details of how we do this 2-bit quantization, because when you do the 2-bit quantization, so you get the accuracy loss. You also, the GPU that you have on the robot performs 8-bit operations. So therefore, there is a process of the reading 2-bit from the memories, unpacking them to 8-bit, so they can run on the jet sonnery, and then again pack them to 2-bit to write them back to the memory. So that's basically the part that I'm just saying, that when you run with the off-the-shelf hardware, you have to actually get into deal with the actual hardware kernels and operation to get the best optimization. But the key thing here is this. So with all these type of these three basically innovation or kind of reduction, it's basically we are making the original model size, which was about 448 meg, to the 10 meg size, which basically the smallest model that's even smaller than the original ResNet convolutional neural network. And we overall, we get about 20 times better energy efficiency compared to non-optimized architecture. So since we are running a little towards the end, what I want to show is with this last piece is system integration. So now you have a tiny large language model. You have also a tiny vision transformer model. Now what is left is basically put them all in the robot. But then robot here, what we are talking, we want to make the robot interacting with you, go to maybe different environments, potentially find what is available, for example, in your kitchen, bring it for you, or if there is an elderly, for example, help what is left, for example, maybe glasses, find the glasses, find the remote, and all those things. So that's basically what is our latest work, which is called adaptive landmark acquisition using large language model guided navigation on the edge. And the idea for Atlas is basically similar to the way that your brain works when you go to a new, for example, house or a new office. While as you're moving around the environment, you gradually remember the location and the type of the objects is in your environment. For example, as the robot is going to the office, it remembers that there was a couch. So next time when, for example, I ask the robot to go and find the couch or go and sit near to the couch, so it knows where was the couch. So similar to this idea of the brain-inspired navigation and landmark acquisition. So that's the Atlas, but then also as I said, the other key parts is that how you can integrate these tiny LLM model and how you can improve the accuracy of these on these robots. And then also my students perform a lot of different data sets and benchmarking to make this particular work, which we call it embodied robotic, running in the house, which is basically currently is the kitchen and the office space. So again, this slide shows a lot of parts of the whole system. But again, let's just get back what the system is. The robot sees what it's similar to us, so the camera input goes. The user input, which is what basically I command the robot, like my pet, to go, for example, find a person, go to the kitchen. And that goes to part of the LLM, as part of the prompt, where basically the language model, which could be any of these tiny models or the large models, potentially perform in terms of the both reasoning and help with the navigation. And then the part that we have it also, which I'm going to talk a little, is that the optimization of the prompts through KB caching to improve the memory. But the one key thing that I want to show in this work is that, because everything that we talked, obviously we said the LLMs, so usually they perform less when you make them smaller. So now what I'm showing is that with few-shot learning, basically giving some examples of this particular task that we want to do, how we can improve the performance while we're still keeping or maintaining the size of these models small. So starting with this left plot, it just categorizes the couple of these models, which are, I call them kind of more on the cloud size because they're large and they cannot fit on these robots. And then the tiny models, which are kind of more on the edge or tiny size. And as the key thing here is that the accuracy is significantly degraded, whereas the cloud model for this type of task. So by showing a couple of examples of these tasks with one-shot learning or five-shot learning, the point here is that you can improve the performance these models. So therefore, you basically get back to relatively almost the same performance of what basically the cloud model were. And that's basically where we use these type of models. So basically we use Qwen and Llama. And here's what I want to kind of wrap up this talk with this very nice demo that my students put a lot of effort for this robot. So there are a couple of key things that I want to show. One is that my PhD student Mikolaj talked with the robot, very natural interaction here. the robot sees what is in front of it, and as it moves, there is a map of the basically my lab. This is my lab here at Johns Hopkins, where we initially mark maybe 3 places: kitchen, home, and workspace. However, when the robot gets instruction by Mikołaj to go, for example, to home or workspace, it also figures out there are some other existing things, like, for example, there is a mannequin stays here. So it will add that to its brain map. Okay, so next time when Nikki asks to go to the person, it finds that it directly goes there because it found it before. But then also more importantly is that the power consumption of the entire system that is basically measured in real time. And you can see that every time that there is a prompt that is passed to the GPU of the ROM, so there, and the action that is generated, there is a big spike. And obviously when the robot starts also walking around, you see there is a power consumption that there changes. Okay, so I run the model. Oh, sorry, let me actually see. Okay, here.
Hi, how are you doing today?
Hello, I'm functioning just fine. Thank you for asking. How can I assist you today?
It's great to meet you. What can you do for me?
I can help you navigate through your environment, provide safety checks, assist with tasks, and answer your questions. What specific assistance do you need?
Could you please go to the workspace?
So as you can see, it found a person as it was going to workspace.
Reach the destination.
Thank you so much. Now head over to the person, inspect them, and then go to the kitchen.
So now it found the person, so it goes to the person. LLM, it breaks down the task, navigate to person, inspect person, navigate kitchen.
Reach the destination.
And now the next task is basically going to kitchen.
Reach the destination.
Thank you so much for your help. Have a good day.
You're welcome. Have a good day too.
Great. So as you can see here, the key thing here is that obviously the power consumption of the large language models, even though these are the small ones, as I just said, so we made them small. We basically improve the performance by examples that I just showed, and but there's still significant power consumption. And basically this shows a little of the more breakdown of where the power comes, because as I just said, the two key operations that is happening on that particular CPU GPU of the Jetson Orin is the YOLO and the large language model. The actual robot that is walking is running on another basically system. So this is just the computation of the parts that we discussed. So the LLM on, YOLO on, the LLM on, so depending on what will be the amount of basically interaction, amount of the action generation and the prompt is, so this basically that much the delay or latency takes with that much of the amount of the power consumption. And then since we are also we use some KV caching, it basically saves some memory transactions, so it actually improves some power consumption and definitely on the latency. So I want to conclude with a couple of key points and the future directions that for those of you are interested in looking at it. So one is that we all know that the future of the AI is not just intelligent. So it's brain-inspired, embodied, efficient, acting in the real world. And for us as a hardware system and circuit design and again, hardware algorithm co-optimization is very important era for us to come up with the novel architectures that can come with a co-design across hardware algorithm and systems. As you can see, that existing, so hardware architecture like these GPUs are not necessarily efficient for this. So you need to come up with this type of models. And as you know, so energy efficiency and memory is becoming a very key constraint in these type of advanced AI and physical systems. So it puts us in two main things. One is that unconventional hardware and memory architecture are critical enablers. And also, as I mentioned, brain-inspired solutions that it can allow to figure out that how basically the brain works, how basically it becomes super efficient in terms of the processing, storage, and make it so adaptive and scalable is extremely important for us as the circuits and system society to enable the next generation of the physical system. So with that, again, I encourage you all to think about cross-disciplinary collaboration to enable this high-impact research. And I would like to thank all my students who did extremely significant, great job on all of these works, but also generous support for the funding agencies. Thank you very much.
Thank you for your wonderful talk. And we already have some questions in the Q&A.
Sure. All right. So let's start. Okay, so I'm gonna start from the beginning. Do you have an algorithm and framework for design space exploration? Actually, really good point. So first of all, I wanted to mention that our framework, especially the bitmap VIT, is already available by GitHub. In fact, it's being already adopted by some other organizations. So I would be really happy to share again the links of the available codes. The large language models we are about to post it, but the very good question that was asked from the Giovanni is for the space. And in fact, our recent work, which we are presenting in DAC this year, we are showing it for the space exploration. And there is actually key a challenge for the space. Two things. For example, if we really want to use these high resolution images that is captured by the space, for example, say drones or some other aerial vehicles, they are very tiny things that needs to be figured out. So therefore, the accuracy is a very important aspect. But also, if we want to do the decision making on board, we are always dealing with a very limited memory size. So therefore, our work on the new DAC paper shows that, and I will be happy to share that with you. Yeah, very good point. The second question by Giovanni, actually, most of them, is it because that all of them from Giovanni, or no, it's just because all the questions from one person? But again, I'm going over the question. So the second question is about the split algorithm, which I briefly introduced. Basically, it's the message passing algorithm, which can be used for fully connected. And again, it's a very good point. Potentially, yeah, so because in a split algorithm, we used the information that was processed for every sub graph of the whole architecture, and pass the minimal information between these subgraph. And potentially, yeah, so I would say it might be used for multiple of these distributed agentic AI. Third question. So why MED-VIT large has poor accuracy compared to MED-Mamba B? And in fact, I didn't go over the work that we showed on the the Mamba and the VIT architectures. So I can again quickly show the question is here. So why the accuracy? I think it was a little confusion because I think you're asking about this MED-VIT, but the MED-VIT2 and the MED-Mamba are have the highest accuracy. And in fact, we both, although these two work are from another other contributors, but we both work both on the vision transformer and the Mamba architectures. Yeah, Mamba, because there could be many reasons, you know. So, but it's a state space model. They perform well in many different architectures, and we recently published it on the T-Biocast, to be published in T-Biocast, that we showed that Mamba architectures also perform really well in this type of data sets. But then again, with Mamba, the same challenges come because as you see, so the size of the memory is relatively model size large, and how you can actually optimize Mamba architectures, and that's the topic of our recent journal in T-Biocast. So getting back to the question, right? What was the last question? Oh, there are a little more questions, so I'm gonna quickly actually answer each of them. Dr. Joe Cavallero, and for smaller models, thank you very much for joining the talk. For smaller models, say time series on a sensor network, how would these tools adapt to, say, an FPGA or small embedded processor with neural accelerator model? So I think it's a very good point. So again, if I understand your question, so you're talking about because before basically jumping to this MED or this vision transformer, we did a lot of work on the time series work. And for example, here, if you just think about any of these images, and in terms of this time series, could be different sensor model, like activity monitoring, or for example, oxygen meter. So the way that we did it, which comes from my student earlier work a couple of years ago, we designed this sensor net, which was actually the topic of my NSF Carrier Award, that how we can make these time series signals, either single dimension or multi-dimensional, like the EEG signals, how we can use the convolutional neural network, and how we can use these overlapping windows for the that we can use it for the convolutional neural network to, first of all, process these multi-modal time series sensing signals. But then once we do this, then it comes again with this type of architectures, that optimization that I just mentioned. So I'll be happy to talk about that offline. And I think there were two more questions, right? Oh, good. There is a question about fine-tuning LLM. It's basically it's when it comes with the LLMs, it's always, especially for the academies, it always becomes very difficult to find the resources in terms of computation. And I believe we fine-tune it with the Alpaca, and I can just quickly look at the slide, as well as the Wikitext. And then that was one data set that we used. And as I just said, in the in this the medical domain data set that I showed, we did it with the MedQ and MedQuad and medical Mido. And these are all available data sets. As I said, I'll be happy to share the code for this. I think there were one or two more other questions in memory computing, right? Yeah. Yes. That's true, right? So in-memory computing, it can, and that's what basically I was going to direct it to that, right? So in-memory computing, spiky neural network. But the point here is that because we have done a lot of work on those type of things, spiky neural network, but the accuracy, as I just said, in the robots or physical system, the accuracy is a very key enablers. For example, if you want to use these medical robots for medical surgery or for the situation awareness or for the case that I was just showing over here, so it's not like an 1 or 0 type of operation. It's a lot of high and reliability decision making, and that's where the challenge is, which I believe they're not as advanced yet. Can robot distinguish between mannequins and real people? Okay. Yeah, of course. Those are very important and questions. And from, in fact, there's a very advanced meant for the visions, vision work in general, so therefore we can use, and the reason we didn't use mannequins is because of a lot of other things, like when you put the human in the pictures, so it's not actually good, so, and sometimes you need an IRB. Lastly, I think that's it, right? So I answered everything. Yeah, beyond medical application, what other end markets do you think LLM compression will find traction? It's, as I said, I believe that because now this multi-visual language models or language models, whether we like it or not, so it's going to be in every type of decision making. And in fact, the approaches that I just showed is not necessarily for the robots, because, for example, right now we are initiating a work with Amazon for the actual their hardware, so the bigger hardwares, and these type of large models, they are also bringing so much of the cost for running the inference, for example, on these even large GPUs. So any type of hardware and algorithm co-design that can bring down the model and operation size and improve the energy efficiency and latency is a very significant accomplishment for us as people that are working in circuits and systems. So I think I answered all the questions. Again, thank you very much for inviting me, Bo and
Thank
Samantha.
you so much. We have very hot Q&A sessions, and also
Thank you.
yeah, and also thank everyone to attend our this month's CAS-wide webinar, and see you next time. Thank you, Dinesh. Have a wonderful day.
Thank you very much.
Thank you, everyone.
Have a
Bye.
great day. Bye.